Thank you for tuning into this revision zone video. This is part 3 of the energetics topics. We're going to be looking at calorimeters, assumptions that we have to make while using them, the errors that it introduces, and a separate required practical, which involves using a calorimeter. So first of all, we're going to jump straight into what a calorimeter is and why we use them. So a calorimeter is just a piece of equipment which allows us to measure the temperature change of a reaction. Okay, so equipment to measure change in temperature. But why do we use them? We use them to be able to calculate the energy transfer in a reaction. There are many types of calorimeters which we could use, and typically there are 3 types that you will need to come across. However, each of those have a different set of accuracy, and the type of calorimeter we use is dependent on the setup required for the experiment, and as a result will impact the overall accuracy. And we're going to be looking at what those calorimeters are here. So the accuracy is dependent on the type used. Now this one that we've got on the left, so this one on the left is actually a copper cup calorimeter, and we use that for combustion reactions. So if I wanted to look at the energy transfer during the combustion of the fuel, look at the enthalpy of combustion for a fuel, this would be my fuel here. I would have whichever fuel I wanted to burn at the bottom, a copper cup, which is this bit here. So that's a copper cup. I'd have the water, and typically this is what we will use because that's specific. We use the specific heat capacity of water, and IQ equals mc delta T, if you remember. And obviously we have a thermometer. Now, this would be the setup for a combustion reaction. We would try and keep that copper cup calorimeter as close to the flame as possible. And this does introduce a few errors, which we'll look at later. This one in the middle is the polystyrene cup calorimeter. Now this is quite a common one. We tend to use it for exo endothermic reactions. Anything that involves reactions within solutions is typically what we use this for. We should always put a lid on the top for any one of these calorimeters, but that again reduces one of our errors that we'll look at later on. You'll see another container around the polystyrene cup, and that is just basically a beaker. Now, the beaker traps air around the polystyrene cup, which acts as an insulator, and we'll see these in other videos. Okay, but it also adds stability so it doesn't topple over. So there is that element there, but the main purpose is to add insulation to our polystyrene cup calorimeter. Now, these 2 calorimeters introduce, well, there is quite a lot of error there, but the way we can remove that is by using a bomb calorimeter. It's quite an expensive piece of equipment, but it really reduces the errors that we would otherwise get with these first 2 calorimeters. So let's have a look at the errors that we do need to account for at A level, and we do need to know. The main error is pretty obvious, is heat loss. Heat loss to surroundings. That's the main one. All right. Second one, if we're looking at combustion reactions using the copper cup calorimeter, it's incomplete combustion. So that basically means I'm going to get soot or carbon monoxide from a combustion reaction, which means that not all the fuel is combusted properly, or fully, I should say, in excess oxygen. So we don't have complete combustion. So incomplete combustion is the other one. This is a bit of a strange one. You might not have heard of this. This is flame disturbance. Now, flame disturbance basically means if you have a flame, that's a dodgy looking flame, but there we go. Okay, on a burner, that draft coming through kind of moves that flame around. That's flame disturbance. Final one, a bit hard to describe, but it's again for the copper cup calorimeter, it's the conduction of heat from the copper cup calorimeter, so the copper calorimeter. And what I mean by that is not all the heat that we, just get that in, not all the heat from our reaction is being transferred to the water where we are detecting the temperature change. Now, all these errors that we've mentioned here make the reaction, or sorry, not the reaction, the energy change, the enthalpy change becomes less exothermic as a result. If we're looking at combustion enthalpies, and this is essentially, or 1, 2, and 3 are all related to combustion enthalpies using the copper cup calorimeter. Heat loss surroundings applies to all our calorimeters. So it becomes less exothermic, meaning the value is less negative. Just a point worth making here, minus 200 kilojoules per mole and positive 200 kilojoules per mole. Neither one of these is bigger than the other. A lot of people will think, oh, negative number, minus 200, it's got to be less than plus 200. That's not the case. The sign does not give you an idea of magnitude. It only gives you an idea of direction. So just keep that in mind. So when I say less exothermic, I mean less negative. So how can we improve the accuracy of our calorimeters? And if we look at copper cup calorimeters first, the first thing we can do is we can add draft excluders. Okay, so draft excluders basically just shield that flame, stop or reduce flame disturbance. The next one could be used for copper calorimeters or any other calorimeter is just quite simply to add insulation. Okay, so you can add a foam layer around your calorimeter, as long as it's not a fire hazard if you're using a copper cup calorimeter, but if you're using polystyrene cup calorimeter, you can add another layer of insulation. For both of those, you would also want to add a lid as well to stop that transfer of heat to the surroundings or loss of heat. The next one to look at finally is a bomb calorimeter, which we briefly showed at the start of this video. Now, bomb calorimeter is a special device which reduces heat loss significantly. So first of all, we can see this diagram here. We have insulated, double layer insulated container. Within that, we have a vessel with water. Within that, we have another container where the reaction is actually taking place. And that reaction taking place in the center here will release heat to the surrounding water, and we have a stirrer to get a uniform temperature change, a uniform distribution of the heat, I should say, energy. We also, and something worth consider here, is it's done under excess oxygen, so we make sure we have complete combustion during any reaction, so we don't have any incomplete combustion. It's also done under pressure, a constant pressure as well. Now, a bomb calorimeter can also measure the amount of heat loss otherwise taken place during a reaction by just using these ignition wires to measure the same temperature change as we have just done with a chemical reaction, and that we can measure the difference in energy between those two values and therefore get heat loss. But all in all, the main thing is to understand a bomb calorimeter is a specialized piece of equipment which reduces heat loss and can get very accurate energy changes or enthalpy changes. Okay, so this is something really worth remembering. So that these things that we've written around improving accuracy, make sure you learn them, make sure you know them. So the next thing we're going to look at here is the required practical, measuring energy transfers and estimating the maximum temperature change. This experiment you will do as a required practical at school. And the key thing about this is getting a method, or knowing a method which allows you to estimate or achieve or approximate a maximum temperature from drawing a graph, which you probably will have already seen at the bottom here. And then we'll be looking at that in a moment. So firstly, just to outline the experiment that you typically would do in this particular situation. It's normally just a displacement reaction of zinc and copper sulfate. And it's a simple equation, no balancing required there. We'll put state symbols in, always worth putting those in. Now we know that we're going to find ourselves with a red precipitate. It's worth mentioning that you're going to use a polystyrene cup calorimeter here. That's the other thing that you need to be able to do. You need to be able to select the appropriate equipment when doing these practicals. So you'd use a polystyrene cup calorimeter, lid, stirrer to ensure a full reaction. We also, which we will have looked in previous videos, we need to have one in excess and we need to have one in as a limiting reagent or limiting factor. Now typically this is normally, it could be either way. This is normally the excess, and therefore this would be my limiting factor or reagent, and that particular quantity we will use to work out the enthalpy change. But we're not focusing on that just here, we're focusing on the actual collection of data. So what you do is you would add a particular volume of copper sulfate into a polystyrene cup calorimeter. We just say that's our calorimeter. Let's say 30 centimeters cubed. And we can use 1 molar concentration. We add an excess at the right time of zinc, but we don't want that just yet. So what we do here is we get a thermometer. We measure the temperature for the first 2.5 minutes. So record temperature for the first 2.5 minutes every 30 seconds. Okay. And then on the third minute, we add our zinc. So for the third minute, you will not have a value of temperature to record. And that's really quite important. And then as soon as you hit the 3.5 minutes, you carry on recording your temperature from 3.5 minutes onwards. And you can do that all the way up to 10 minutes. But essentially you need several results after the temperature starts to decline. So 3.5 minutes every 30 seconds for 10 minutes, let's say. Okay, and we continue to do that. And what we then do is we plot our graph. So we end up with a graph like this. Now the annotation's already in there, but we'll just talk through it. So here you've got that initial temperature for the first 2.5 minutes. So you can see that this is our final reading at 2.5 minutes, and you'd expect it to stay roughly the same because you're allowing your initial solution to attain the temperature of room temperature. And then on your third minute here, you add in your zinc, and remember that's in excess, and you see the temperature from the 4th minute here. I feel like they've recorded that a little bit earlier than 4 minutes, but you can see that it's increasing nonetheless. And then we continue that measurement every 30 seconds until we feel that we've got enough results here, and we can go up to 10 minutes. I think this one is about 9 minutes. Okay, but we could go up to 10. We could keep going until we achieve these these previous values or initial temperatures, but there would be no point. That would be quite a waste of time. But anyway, once we've got that data, now this is the key bit. We must draw 2 lines of best fit. Okay. Now, the first line of best fit is for these initial temperatures here. I'm going to just extend this out a little bit so you can see that a bit more clearly. Okay, so we extend that out. The next line of best fit we draw is for this declining or negative correlation data here. So that's where we draw our second line of best fit. But what we do is we extrapolate, so we don't curve around this point. We don't want to curve, we just want to continue that straight line backwards, and that's called an extrapolation. It's called an extrapolation, and we continue it going back, and it needs to go past the 3rd minute point. Okay, we then add a dotted line, as you can see here, which I'm going to highlight. And the difference between these 2 lines of best fit is our maximum temperature change. So this is our maximum temperature change. And that accounts for some of the energy loss that we'd otherwise have, but also accounts the fact that we can't measure maximum temperature change because we have this curvature going on. And it's this value here that we then use in Q equals mc delta T to calculate the energy transfer and then calculate the enthalpy change, which, remember, is Q over the limiting moles. The limiting moles in this particular situation for myself is a copper sulfate, but always be mindful of which one you have calculated to be as excess. Just remember to put your sign in at the end if it's extra or endothermic, and units and any accuracy as well. So that's the required practical in a nutshell, which you will all be doing. And it's definitely worth knowing this for the exam, because these are the purpose of the required practicals, is to make sure you have an understanding of how to apply knowledge, how to carry out the practical, and what to do with the data as well. That concludes this video. I hope it was useful. If it was useful, please hit the like button and subscribe and stay up to date with our new videos. And use the comment section to let us know what other videos you would like to see. Until next time, take care.